Okay, here folks, we're going to look at 2007, question 9, part A. So this is a nice little normal hydrostatics question where we have a U-shaped bend in it. Okay, these ones are actually fairly easy to do once you get your head around them, and they can be head-wreckingly annoying to look at the marking scheme and try and figure out backwards if you don't know the way they're put together. So let's have a little look at this one. YouTube like this, and nice little diagrams are good kind of benefit to this one. So we'll get two big diagrams there. There's one, and we have our liquid there and there, and that is of course mercury. So rho is 13,600. Okay, now you can do a little bit of decoration. This, I mean, I know it sounds trivial, but you know that that's empty. Okay, we add a load more stuff into it. So let's have a look at it next. So this is before, and this is after. Now, what's going to happen? Well, first of all, actually, we had 26.2 centimeters there to there. We're going to pour a load of stuff in, a load of water. All right, that's going to displace the mercury, and it's going to go down to maybe there. All right, so if we just bring across a little bit of a dashed line to compare before and after. Okay, so that was the original level. So the mercury goes down. Now, liquids aren't compressible, so the mercury has to then go up on this side to balance. And this is all water. All right. So that is rho 1000. And that's still mercury. All right. So what we're going to do is basically, this is still, of course, that's 26.2 there to there. And let's call this little distance here to here x. All right, which means that this has gone up by x, which means the difference in heights here, this is where people get confused, is 2x. All right, now what I'm going to do is we're going to now solve this one by looking at pressure. Pressure in the liquid is basically equal to everything pushing down on it. Okay, strictly speaking, we're going to look at the force on it because the area of the two is going to be the same. So if you think of it, pressure is force over area. So P1 equals P2, A1 equals A2. It's the forces. So we're going to look at this in terms of force just to make life a small bit easier. I'm going to take the pressure at this point here. All right. Now, what have I got above each side? Well, on this side, okay, the left-hand side, I've got all this water. So basically, we're going to use the equation here, which is V rho G. Okay, V rho G. This is going to be the right-hand side. Now, V, of course, is the area by the height in rho G. Now, what have we got here? So let's say the area by 26.2 plus x. Now, for my units, I'm just going to stay in centimeters the whole way around because we're looking for an answer in centimeters. Okay, we want to find x in the end. By rho, which in this case is 1,000, by g, and that is the area. The area of both of these sides is the same, which is going to be nice. What's going above it here? Well, it's 2x's worth of mercury. And that is, of course, rho 13,600 and g. So now that we have this laid out, okay, so we're looking at the force pressing down at each point. Strictly speaking, we're measuring the pressure, but like I said, the area is the same, so it cancels out to the force. Let's cancel out a few things here. The area can go each side, and g can go each side. Okay, and actually the 1,000 can go, and that becomes 13.6. So that is 26.2 plus x equals 2x by 13.6. All right, 26.2 plus x is multiply that by 2, and you're going to get 27.2. You see where this funny number came from? X. Take x from both sides. 26.2 equals 26.2x. X equals 1. And there you have it. Okay, so they're quite nice little ones. There's a few different ways you can go about this one, but the key to all is really realizing that if this goes down by x, that goes up by x, and now we have 2x sitting above it. You get that right, and it falls together really nicely.